In Concept C today, we're going to focus on two types of nuclear reactions, fission and fusion, and a little bit about their application. So your target for this lesson is to be able to compare and contrast fission and fusion reactions, whether it's just discussing the main points about them or actually analyzing different equations to figure out which is which. We're also going to be talking about something referred to as mass defect. So I want you to be able to explain what mass defect is and also how matter and energy are affected in a nuclear reaction, especially compared to regular reactions that we're going to talk about the rest of the year. So first we're going to speak about fission. This is the splitting of the nucleus of an atom. So the larger particle is going to split into smaller particles. The most classic example is uranium, and we're going to see that it's going to, once it's combined briefly with a neutron, it's going to become unstable and then split, releasing a large amount of energy. So if an isotope like uranium is hit with a slow-moving neutron, it can capture that neutron, making a very unstable intermediate nucleus, and then because it's unstable, it's going to break down into several fragments, which releases a huge amount of energy. And then more neutrons are always produced. So you can see here it's going to get hit by the slow-moving neutron. There's an intermediate unstable nucleus that forms, and then it splits into two separate atoms, and then producing here 3 neutrons and also energy. Now this is important because this is why we can use this in a nuclear reactor. Our 3 neutrons that get released can cause 3 other uranium-235 nuclei to fission, producing 9 neutrons, which then go on and hit 9 other nucleus. So now we have 27 neutrons, and then 81 neutrons, and so on. So this is the start of a self-sustaining nuclear chain reaction. Now we can do 2 things with this type of chain reaction that we'll see in the next slide. Here are 2 examples. I want to point out a couple of things because you have to be able to identify a nuclear fission example. You'll see we have uranium. We could also see something like plutonium here. We always have a neutron to the left of the arrow with that very large nucleus. We're going to see that it breaks up into 2 different and new elements. And then another key part to this is that we always produce either 2 to 3 neutrons, which again would go on to continue the chain reaction. Now, if this is an uncontrolled chain reaction, it's going to release huge amounts of energy, and an example of this is the fission bomb, which is more commonly known as the atomic bomb. However, if we can control that chain reaction, we can actually use it as a continuous source of useful energy. So we'll talk a little bit more in class about a nuclear reactor and how we're able to use fission. Some things I always like to point out is we think of these shapes of the buildings as the reactor, when actually that's just really the cooling tower. It's the containment buildings where fission's actually taking place. You'll see that it has control rods, and the point of those control rods is to control that chain reaction. And again, one of the other things I like to point out to students that they don't realize is they're using the heat and the energy released from the reaction to actually heat water, and it's the steam that then goes and spins the turbine, generating energy. And again, we'll come back to this a little bit tomorrow, but I do want you to realize some advantages and disadvantages. Some advantages to nuclear reactors is not giving CO2 or commonly known as greenhouse gases. It has a high power output because of that continuous source of energy. The cost of the fuel source is effective. We only really need a small amount of uranium needed. There's no fossil fuels involved. However, some drawbacks and disadvantages is thermal pollution that's putting out into the environment. It's a very high initial cost to build these nuclear plants. There is hazardous nuclear waste that are produced after that we have to be able to store and take care of. And we've seen in history some situations that because of negligence, we've had a harmful breakdown or disaster at a nuclear reactor. Alright, so now we're going to move on to fusion. This is where instead of splitting the nucleus, we're going to combine them to form a heavier nuclei. So we're going to have light nuclei, usually hydrogens, heliums, maybe we'll sometimes see lithium in our examples, which are going to combine to produce, again, a heavier nucleus. So here are some examples. In this case, we happen to have hydrogens as our 2 products. And again, here you can see that they're combining into a helium-4 nucleus. On the bottom, again, same idea, except because of the masses of the hydrogens, we end up with this extra neutron. So again, I'm going to show you a bunch of examples. The big thing is you're always looking for 2 light nuclei on the left, combining to form a heavier one on the right. So fusion is how all stars produce their energy, including our sun. We're not just talking about hydrogens and heliums combining. On the sun, there's also various other types of fusion reactions occurring. Now, fusion reactions require very high temperatures to cause those positively charged nuclei that want to repel each other to actually overcome those repulsions and combine. So just something to keep in mind why this is able to happen on our sun is because of those high temperatures that are provided there. For the same given amount of fuel, fusion actually gives off more energy than fission, and there's a lot fewer pollution problems. Instead of dealing with a very radioactive uranium, we're just dealing with hydrogen and helium, which would be safer to handle and store. However, because of the high starting or ignition temperatures, we haven't been able to successfully use a fusion reaction in a reactor. However, you'll see, I've seen in the news a lot the last couple of years where they're getting closer to that, also coming up with something called the cold fusion reactor and so on. So it's not too far away in our future that this could actually become a reality. Now, one thing that we have seen in history where fusion was used was in a hydrogen bomb. So this is actually started by a fission reaction, which provides that high ignition temperature, which then allows the fusion reaction to occur. So where is all this energy coming from with these fission and fusion reactions? One thing is something called binding energy. We have a tremendous amount of energy that actually has to hold all those nucleons tightly together. When we change or rearrange the nucleuses or nuclei, that energy is released and is a huge amount of energy. Which is one of the parts of these fission and fusion reactions giving off the amount of energy that they do. Another very important piece of this, and I would put a big star in your notes next to this, is something called mass defect. The total mass of the products is actually less than the original mass of the reactants. Now, that kind of goes against what we know as the conservation of mass or matter. However, this is like kind of the gray area, because what's happening is the matter, a very tiny amount, is getting converted into a huge amount of energy. So we can account for the loss of matter as energy, which is something completely different than what we're going to see the rest of the year in chemistry. So during, again, fission and fusion, we have this mass defect that takes place where a small amount of matter is converted into a large amount of energy, which results in the mass of the products being a little bit less. This goes back to the kind of the well-known Einstein's equation of E equals mc squared. This basically proved that particles of matter, if we're able to vibrate them at the speed of light squared, they can be converted into energy. And again, this is going to be very different than the rest of the year where we really do follow the conservation of mass and energy. But for these fission and fusion reactions, again, gray area where we're actually converting it into energy. Okay, that's it. We're going to go tomorrow into some examples, hopefully watch a video related to this as well.